So everything is fine, right? Okay. Okay. Yeah. Sorry for all the technical interruptions, and thank you for holding on to this. So as I was saying, um, I will be talking about brown dwarfs and exoplanets and what JWST can do with us. Um, so the James Webb Space Telescope is already launched. It has completed its calibrations mostly. And on July 12th, the first data is going to become public. And if you're interested, you can take a crack at analyzing or reducing that data set. Okay, but the question is, why is JWST very relevant for exoplanet and brown dwarf science? Why exactly are we talking about JWST in an exoplanet talk? And the reason is because of its wavelength coverage. People generally think of JWSTs nowadays as a successor to the Hubble Space Telescope. But the HST is mainly an optical near infrared, near ultraviolet telescope, whereas JWST is a totally infrared telescope, even though it can cover some of Hubble Space Telescope's wavelengths like optical, but its primary design is optimized to work on infrared wavelengths. Now, why is that important? The reason is basic physics, which is if you go to the Wien's law and you take the temperature of a typical planetary atmosphere or a brown dwarf atmosphere and you calculate that at what wavelength the most of the thermal light goes out from the planet using your Wien's law, then for an Earth-like planet, it comes to be about 10 microns, which is mid to far infrared. So that means for all these colder planets and brown dwarfs, JWST is perhaps the perfect observatory to study them because it can really sensitively detect infrared light, which most of these planets emit. Now let's talk about exoplanets. What are extrasolar planets? Basically planets which are outside our solar system. Any planet which is not bound gravitationally to our sun can be called an extrasolar planet. These can be rotating around other stars than our sun. These can be free floating alone lonely planets as well. So extrasolar planets are planets outside our solar system. And in this animation, you basically see a direct image of 4 extrasolar planets rotating around a star. The star has been blocked out because the star is much brighter than the planet, so that you can see the dim faint planet. And you can see these blobs of light rotating around. And these are rotating around a star called HR 8799. And what you see here, the light from the planet is its thermal emission, that light it is emitting due to its own temperature. But why study these faraway worlds? These are so far away that we do not have a realistic, optimistic hope of ever visiting them. Then why do we study these planets? And I like to think of the motivation in 3 steps. The first is to understand their atmospheres. We have, for the past 40 to 50 years, explored our solar system quite well. We went to Mars with our robots. We went to Jupiter with our probes. So we have a basically good understanding of our solar system atmosphere. It's not perfect, but it's better. But what about the atmosphere of this other world? Do they host atmospheres? If they host atmospheres, what is their composition? How is their composition different from our solar system atmosphere? So these are all questions which are very intriguing, and we must answer this question. But there are other reasons to understand planet formation. Earlier, we had developed some planet formation theories based on our solar system, but our solar system has only 8 planets. To constrain any theory, you need statistically large samples. Where do you get that? We have already discovered 5,000 exoplanets. So if you have a theory of how planets form, it should work for all these exoplanets. So exoplanets are a great way to constrain your planet formation theory because they are still there is a lot to be understood about planet formation still. So this is another motivation. And the third, and perhaps the final frontier of this field is to find another Earth-like planet, or the Earth 2.0. Can we find another Earth in our universe? If we can, does it host life? Is it habitable? If so, what kind of life? Can we detect that life? So these 3 goals, I think, are intriguing and compelling enough to tell you that why you should be excited about this field, which is just 20 to 30 years old. It's a new field. What today I'm going to talk to you about is how is the first goal to understand their atmosphere. My entire work is to trying to understand the atmosphere of exoplanets. So let's take a brief walk down history. This plot is an animation. It basically shows in the y-axis the mass of exoplanets we have discovered in units of Jupiter masses. And in the x-axis, it's showing you the period, the orbital period of those planets. So the x-axis is a proxy for the star-planet distance, and the y-axis is the planet's mass. And starting from 1990s, we have populated this parameter space with many exoplanets with different techniques. I won't go into them, but if you're curious, you can ask me later. But yeah, we have populated this entire space with many exoplanets. And what have we found? We have been utterly surprised with some findings. For example, okay, something is happening. Can I not? Okay. Yeah, I don't know. Anyway, yeah, there was this plot. Imagine that plot here. And what we found was perhaps the most surprising thing was hot Jupiters. These are Jupiter-like mass planets. So imagine a Jupiter, but they are very close to their host star within the orbit of even Mercury. So we did not expect to find this planet. How did this planet form? We still don't know very well. But when we looked out there for the past 25 years, we found a lot of hot Jupiters. We also found distant giant planets, Jupiter-like planets, which are separated from their stars by hundreds of AU. We also found sub-Neptunes and super Earth-like planets, so planets which are much smaller than Jupiter, but larger than Earth. So we have this whole population of planets over the years. But this is all about detection. Detection has been happening for the past 25 to 30 years. But now we are thinking of taking one step forward and trying to really understand these planets and not just detecting them. And let's see where we are at. Yeah. Oh, I need to click sometimes. Okay. Okay. So let's see how well do we understand exoplanets today. So in the top left, what you see is a spectrum of Jupiter, but from 1969. So almost 60 or 50 years ago. And you can see that the data quality was not very good back then. And in this plot, you see the spectrum of an exoplanet, but which is today. And you can see that's comparable. So what we understood about Jupiter back in 1969, when we were trying to land on the moon, is what we understand about exoplanets today, which means that our understanding of exoplanet atmospheres is basically running 50 to 60 years behind our understanding of solar system atmospheres. So we do not know a lot about exoplanet atmospheres, and we definitely need to do better. And that's where brown dwarfs come in. So let me first introduce brown dwarfs, and then I will go into why brown dwarfs are relevant here. So what are brown dwarfs? In one simple sentence, brown dwarfs are basically failed stars. So when you have a successful star or a main sequence star, what it does is it's massive enough that it can start hydrogen fusion in its core, and it can stop its contraction and maintain its luminosity throughout the main sequence lifetime. But brown dwarfs are basically stars which do not have enough mass to start hydrogen fusion. So there's nothing to stop their contraction and to stop their cooling. So brown dwarfs are failed stars. As a result, they keep on cooling and cooling and cooling for millions of years and billions of years. So that's what brown dwarfs are. Now you might be wondering again, why am I talking suddenly about brown dwarfs in exoplanet stuff? And the reason is that brown dwarfs can be really similar to exoplanets. For example, the coldest discovered brown dwarf we know about has a temperature of 250 Kelvin, which means it's much colder than this room. And so that means that brown dwarfs atmospheres can have temperatures similar to that of exoplanets, right? But we have some advantages of studying brown dwarfs compared to exoplanets. let me show you another example of how brown dwarfs are similar to exoplanets. This plot is basically showing you a color magnitude diagram or an observer's HR diagram. The y-axis is the magnitude or the luminosity of your source, x-axis is the temperature. And all these solid points, the red, blue, and violet you see is how brown dwarfs land on this diagram. And the yellow points are how exoplanets land on this diagram. And you can see that they land on pretty similar parts of the HR diagram, which again goes on to show that brown dwarfs and exoplanets can be quite similar. Just a word of caution, I am talking about gas giant exoplanets and not a terrestrial exoplanet here. Okay, so they are very similar. But we can get much better data about brown dwarfs than we can ever do from exoplanets. For example, here you see 3 spectra of brown dwarfs in the top 3 spectrum. And the bottom red spectrum is a spectrum of Jupiter today. Then you can see that we have similar quality of data from brown dwarfs, almost as what we have from Jupiter. But if you remember, our data on exoplanets was quite poor. And the reason behind this discrepancy in the data quality is because exoplanets are around a very bright star. To get data from your exoplanet, you need to suppress that much brighter star. And that's a difficult technique of coronagraphy, which is not now good enough to get this kind of data from gas giant exoplanets. So brown dwarfs are similar to exoplanets, but give us much better data than exoplanets. So it's worthwhile to try to understand brown dwarf atmospheres, which are first of all interesting in their own right. We need to understand brown dwarf atmospheres, but also they will teach us a lot about what to expect from exoplanetary atmospheres now.
Sagnick, sorry, I sort of missed that bit where you were trying to explain why why do you get a better spectra from brown dwarfs than from exoplanets?
Right, yeah. The reason is mainly because your exoplanet is around a very bright star, which is about 10 to the 5 times brighter than your planet. And to get the thermal spectra of your planet, you need to suppress that light from your star. And that is sometimes very difficult to do most of the time. So your data on exoplanets is uncertain. But brown dwarfs, they are just free floating star-like objects, but they are not stars. So they are free floating, they're isolated. There's not a very bright source of light around them. So you can, with some longer integration time, you can get better data on brown dwarfs. Does that make it clear?
Yeah, that does make it clear. Yeah. Are there planets which are also kind of far out or just been kicked out of stellar systems, which can give you an opportunity to observe them in isolation?
Yeah, totally. There are some about 6 to 7 planets in total out of these 5,000 planets we have discovered, which are far enough and switchable enough so that we can get their thermal spectrum.
But of course, the point is, if you're looking for like a habitable planet, you're probably looking for something around a star. So this problem will always exist.
Yeah, totally. In those cases, you need to go into transit spectroscopy, which also makes it very difficult to do. But yeah, you're totally right. Okay. So yeah, we get much better data on brown dwarfs than exoplanets. They are easier to study today, and they're really similar to exoplanets. So let's talk about the physics of brown dwarf and exoplanet atmospheres. And again, I need to put this caution. We are talking about gas giant exoplanets and not terrestrial exoplanets. So let's go into this schematic. I really like schematics. So let's think about the physics of brown dwarf and exoplanet atmospheres. So if you take a look at the typical structure of a gas giant planet or a brown dwarf, 99% of the mass of the object is inside something we call the interior. So it's inside this interior, which is shown in yellow. And only 1% of the mass is in the atmosphere. But the atmosphere is perhaps the most important part in its entire structure. This 1% of mass controls the evolution of the entire planet or the entire brown dwarf. Why? Because the interior has some heat of formation, because it has some gravitational heat. Remember, there's no nuclear fusion, so there's no fusion heat, but there's still some heat coming out from the interior. That heat needs to go out from the object because your object is trying to cool, but your atmosphere comes in the way, and your atmosphere is of such temperatures that you have a lot of gas molecules around. Okay, and these molecules can trap this heat, they can absorb this heat. Not only that, you can have clouds around. For example, Jupiter has methane clouds, and clouds are really good at kicking photons. They're really good at scattering photons. So added to that, you have your host star trying to inject energy in an atmosphere with its radiation. So you can already see that the picture is getting complicated. There are so many different things which are very distinctly different from each other, coexisting in the same atmosphere. Now, added to that, you have dynamics. You have storms, you have cyclones, you have all these weather events, which makes it even more complicated. So your atmosphere, the schematic itself is getting complicated. So let's break that down into some physical components which are easier to understand. So the first component is the temperature structure of your atmosphere. The next component is its chemistry. What's the chemical composition? The next is its radiation. How does radiation travel to the atmosphere? Clouds, and then dynamics. So these, you can think of the atmosphere composed of all these distinct components. But see, I have put in arrows here, which basically tells you that these components are not independent. If you change the temperature structure, everything else will get impacted and everything else will change. Now let's take a look and define each of these things. First of all, the temperature structure. So what do you mean by the temperature structure? It's simply the temperature versus the height of your atmosphere. What's the temperature at each height? And often we, exoplanet theorists, like pressure more than height because it's a more natural coordinate to think about. And you can define it here as, this is showing you the temperature pressure profile of a brown dwarf atmosphere. And higher pressure means deeper atmosphere, and lower pressure means upper atmosphere. And what you see is the deeper atmosphere is very hot and the upper atmosphere is very cold. That's your temperature structure. Now, as I said, brown dwarfs are not rotating around a star. If you have a planet which is rotating around a star, its temperature structure can look very distinct because of that stellar energy. The star is also heating up the atmosphere. And this is how the temperature structure of a typical hot Jupiter might look like. Okay, now let's go to chemistry. These atmospheres are cold enough to form molecules. In fact, they are mostly molecule dominant. You do not have ionized gas or plasma in these atmospheres. So you have got molecules like water, carbon monoxide, methane, ammonia, carbon dioxide, oxygen, nitrogen, name it. And whenever you have these many molecules in the same atmosphere, what you get, and what I don't like much, is a lot of chemical reactions. You get thousands of chemical reactions. So if you're thinking of modeling such an atmosphere, you need to take into account all these chemical reactions which can go on in an atmosphere of a planet or a brown dwarf. Okay. Now let's move on to clouds. Clouds always intrigue me because there is so much diversity of clouds. On Earth, we are generally, whenever we say clouds, you think of this white, fluffy water cloud. But even in our solar system, Jupiter has clouds made up of methane. Okay. Venus has clouds made up of sulfuric acid. Uranus has clouds made up of, again, methane. And some exoplanets are expected to have clouds made up of iron or other rock-like minerals. Just think about that. So clouds can get really exotic. And clouds can impact your atmosphere to a large extent because clouds can heat up, trap a lot of heat. Okay. So clouds are also really important when you're thinking about modeling such objects. And the last bit, not the last bit, but another very important bit is radiative transfer. You have this heat coming up from the center of your, or the interior of your planet. So photons can just pass through your atmosphere and hit your telescope. They can get absorbed by a gas and give you an absorption line. They can get scattered by a cloud and come to you. And they can even bounce between the clouds and ultimately come to you. And all of this physics is taken into account by radiative transfer. And you need to take a good care of radiative transfer in these atmospheres because they are really important. Now let's, because audience has a lot of stellar astronomers, I believe. Yeah. Uh-huh.
How is the lower limit of the temperature defined in the case of brown dwarf?
Okay, so there is no lower limit. It's mostly a lower limit of mass. Anything which is between 73 Jupiter masses and 13 Jupiter mass is considered a brown dwarf. because these objects can burn a little bit of deuterium in their very early life. And those are considered to be brown dwarf. And anything which is lower than 13 Jupiter mass is typically called a planet. But this boundary is very fuzzy. People do not agree on this boundary a lot. But yeah, there's no lower limit on temperature. Okay, so since this audience has a lot of stellar astronomers, I want to show one difference between stellar atmospheres and planetary atmospheres. And that difference comes from opacity. So when you have a star, it's really hot and you have a lot of ionized species, right? And your opacity looks like something like this, like a flat kind of a gray opacity. There's not much variation across wavelengths. But when you start to cool down, you start to form all these molecules, which can lead to 5 or 6 orders of magnitude variation in opacity within a very small wavelength range. So your atmosphere of a planet is not black body. Planets are not black bodies. Stars are kind of black bodies, but planets are definitely not black bodies because of this huge opacity dependence. Okay, that's all about radiative transfer. And last, and my favorite, is dynamics. Atmospheres are not static, even though in our physics courses we are taught hydrostatic equilibrium. That's kind of true, but atmospheres in general always are moving. That's why you have rainy season and all these weather events on Earth. So what kind of movement am I talking about? Oh, the videos are not working. But here I had convection in noodles. So you can have a lot of convection or churning motion in planetary atmospheres. In fact, right where we are sitting, the troposphere of Earth has a lot of convection. Other than that, you can have gravity waves in your atmosphere. This video was of a gravity wave in a cloud on Earth. You could see the cloud swinging in gravity waves. And that also can happen in brown dwarfs and planets. So brown dwarfs and planets can have a lot of dynamics. But when you are studying solar system objects, for example, Jupiter, you can actually resolve the disk of Jupiter because it's close by. You can resolve its disk. You can take this wonderful image in infrared in Jupiter, and you can actually see all the signatures of dynamics, those storms, those plumes, those vortices, those eddies. Even better, which won't perhaps work, yes, there was a video here of those storms happening in Jupiter's atmosphere. But brown dwarfs and exoplanets are a pixel to you. They are a point source to you. So you cannot ever resolve their disk and look at all these vortices and eddies and things like that. Then how do we study dynamics in brown dwarf and exoplanet atmospheres? So that brings me to my project, which is to probe the dynamics in brown dwarf atmospheres or planetary atmospheres. And how can we do that? And why is it so important to study dynamics in these atmospheres? Okay. So the way you can do it, you cannot do it directly. You cannot look at the dynamics directly. But dynamics has some effect on chemistry of your atmosphere. So if you have a dynamics in your atmosphere, your chemical structure can get impacted. And remember, chemistry is easier to measure because you can measure absorption lines well. We as astronomers, that's all we do all the time. So chemistry is easier to measure. And if dynamics impacts the chemistry, we can perhaps measure that impact and tell something about dynamics in these atmospheres. So let's think about this with this ink in a moving fluid kind of a GIF. I'm really thankful that this is working, but perhaps once. But anyway, so think of your atmosphere as a rotating water fluid as it was here. Okay, that's your dynamically active atmosphere. And think of this ink as some gas. Now, once you put this gas in this background atmosphere which is moving, the gas will also start to diffuse with the atmosphere because of this movement. Okay, and that's how atmospheric dynamics can impact the chemistry of your atmosphere. Let's take an example. If you have a gas giant planet between temperatures of 500 to 1000 Kelvin, then think about this gas molecule carbon monoxide. If you have no dynamics, then carbon monoxide is supposed to be confined to the very deep atmosphere from physics. It's supposed to be present only in the very deep atmosphere if you have no dynamics. But once you have dynamics, the dynamics can dredge up all those carbon monoxides from the deeper atmosphere and bring them up in the upper atmosphere. Now, if this happens and you are an observer trying to measure the carbon monoxide in this atmosphere, and you are suddenly surprised that I did not expect to see carbon monoxide here. How am I getting so much of carbon monoxide? And the reason might be that because of dynamics, which is dredging that carbon monoxide up, basically winds in the vertical direction.
Sagnick, so I have a confusion here.
Yeah,
Um,
sure.
if your measurement is essentially 1 pixel, and you're perhaps doing transmission spectroscopy or something like that here,
Um,
how do you resolve uh, uh, height distribution, like a radial profile of any gas?
Yeah, that's a really good question. So first of all, in this case, I am talking about thermal spectroscopy. So you are trying to capture the thermal light of the atmosphere. Now, since the opacities are so wavelength dependent, that means at each wavelength, the light you are getting is coming out from a different
Different
pressure or
depth. I
height.
got it. Okay, thank you
Yeah,
very much. Okay,
yeah, yeah,
perfect.
yeah. So great. Yeah, that was a really good question. Um, so yeah, dynamics can spread around your gases and you can perhaps detect that. Now let's think about this theoretically. Oh, the equation is gone. Okay. Um, so again, imagine a diffusion equation here. I hope most of us are familiar with it. If you want, I can write that out. Is that necessary? Okay, I can just maybe do that. So the diffusion equation is this is the famous diffusion. I hope I have written it right. But anyway, this is the diffusion equation. Now, you can think of this dynamics affecting your gas as a diffusive process, because that's essentially what dynamics is doing. It's spreading your gas around. And that will be described by this equation. And this equation, and so let me introduce the variables here. Your chi I here is the abundance of a certain gas, which is changing due to diffusion. And this KZZ is your famous diffusion parameter, which always comes free with a diffusion equation. Now, with some simple dimension analysis, you can derive a time scale associated with diffusion. So what's the time this diffusion will take to spread everything around? And that time is called the mixing time scale. And that time is inversely proportional to KZZ. Now, what KZZ basically tells you is the strength of your dynamics. If your KZZ is high, that means the atmosphere is really dynamically active. If your KZZ is low, that means everything is static, kind of. And that you can see with the mixing time scale. If KZZ is high, your mixing time scale is small. That means it would take a short time to mix everything up. That means you're really moving a lot. But if KZZ is low, your mixing time scale is really long. That would take a long time to mix everything up. Okay. So basically, we are parameterizing our dynamics on this parameter called KZZ. Okay. So if we measure this parameter KZZ, we will have some idea about the strength of dynamics in that atmosphere. Okay, equations are gone, but let's take an example of this chemical reaction. So this is a reaction between methane, water, and carbon monoxide. This is a common reaction which happens in a lot of atmospheres like of Jupiter. Now, every reaction also takes some time. Reactions are not instantaneous, right? Every reaction takes some time to happen. And let's say that that time is the chemical time or the tau chem. Okay. That's the time it takes for this reaction to be completed. Now, imagine if tau chem is shorter than tau mix, which means your chemistry is faster than your mixing, then you won't see any effects of dynamics, because when dynamics will try to mix things up, chemistry will destroy those things and you get equilibrium chemistry, chemical equilibrium. It's as if chemistry was always winning and there was no dynamics. But if it's the other way around, if your dynamics is really fast, that means dynamics will mix everything up even before chemistry can destroy them. And then you get disequilibrium chemistry. So dynamics leads to chemical disequilibrium in your atmosphere. And that is what is basically was shown here with these basic equations. So dynamics can lead to chemical disequilibrium. Now that means that if you're an observer and you're measuring the amount of CO and methane, and you suddenly realize that CO and methane amounts are such that they're different than what you expect from equilibrium chemistry, that means you have disequilibrium chemistry, that means you have dynamics, that means perhaps you can measure KZZ, the strength of dynamics. Okay, let's take an example of that. So this is the pressure temperature profile of a brown dwarf. The deeper atmosphere here is mainly convective. That means the primary energy transport is happening through motions and convective waves. Whereas the upper atmosphere is radiative, where it means the radiations are carrying the energy. Now in the convective zone, you have a lot of convection. So you have a lot of dynamics. So your mixing time scale would be small because things get mixed pretty easily. Whereas in the radiative zone, the mixing time scale would be large because you do not have much dynamics because most of the energy has been carried through radiation. Now here is a plot of your chemical time scale for this reaction, the methane and carbon monoxide. Now in the deep atmosphere, right here, your chemical time scale is shorter than your mixing time scale, which means chemistry wins and you have equilibrium chemistry. But above this pressure, called the quench pressure, where they cross, your mixing time scale becomes faster. That means the mixing will win now and things will get homogenized above this pressure. And this is called the quenching of abundances. That means your abundance, molecular abundances will get quenched at that pressure. So the solid line here shows you the abundance of CO in this atmosphere if you did not have any dynamics, right? And you can see the CO is falling sharply. You practically have no CO in the upper atmosphere. But if you have dynamics, if you have this quenching, then CO becomes constant above this line. And this is a log scale plot. That means dynamics can cause the abundance of CO to change by 10 or more orders of magnitude in your upper atmosphere. So the amount of CO can become 10 times if you have dynamics, not 10 times, 10 to the 10 times. If you have dynamics compared to when you do not have dynamics. Let's see the observable here. What you cannot make this plot because this is a model. What do you see as an observer? You see the spectrum. Now this is showing you a spectrum of a brown dwarf. You can see all these deep absorption. So you can immediately see this is not a black body, right? A spectrum of a star does not look like this. This is very different than a black body. And you can immediately see all these deep absorption features caused by various molecules like water, methane, H2O. Now look at this band called the M band. So orange line shows you the spectrum if you did not have dynamics or chemical equilibrium. Blue line shows you the spectrum if you had dynamics or chemical disequilibrium. And you can see in this M band, which is between 4.5 to 5 microns, you get a large difference between the two spectrum because that's where CO is the main absorber. Dynamics has led to 10 orders of magnitude difference in CO. So you get a very deep absorption of CO if you do not have, if you have dynamics. So this is an observable effect. This is not just theory. You can get the spectrum for brown dwarf, measure the amount of CO from the spectrum, and can kind of tell that what's the amount of dynamics you have in the deep atmosphere of these brown dwarf or giant planets. And this has been done successfully for planets like Jupiter and even Saturn, but not for exoplanets very successfully yet. Okay, so let's see where do we stand about our knowledge of dynamics in exoplanets and brown dwarfs. So in the convective zone, imagine KZZ written here. In the convective zone, we have some theoretical idea about what KZZ should be from mixing length theory. We have some theory there, okay? But things are much worse in the radiative zone. We practically do not know what the KZZ value should be from even theory in the radiative zone. It is typically assumed to be anything between 10 to the 2 to 10 to the 10, which makes KZZ uncertain by 8 to 10 orders of magnitude. This parameter, the dynamics parameter, is perhaps the most uncertain parameter in the entire field of exoplanets and brown dwarfs.
So Sagnick, another question I have is regarding the complexity of the convection zone itself. Now, I'm not sure about brown dwarfs, but certainly for stars or even for planet Earth, if you look at different transport coefficients in the atmosphere. Um, their contributions not only from convection, but there is also large scale circulations, like the Hadley said, right? For
Right.
example. Now, in principle, what you're doing, and I guess and this is because you don't really have any other option.
Yeah.
You are putting everything together in a black box
Right.
of a time scale and calling that a dynamical time scale.
Yeah.
This is really a effective or a mean time scale of everything, including diffusion and circulation or whatever, maybe transporting or mixing the atmospheric constraints up. Is that correct, or are there more sophisticated models
Yeah, that's a great
for
question.
boundary?
So, yeah, so basically you are saying that we are putting our ignorance on a single parameter called the KZZ. Now, what you are asking is how to interpret physically that parameter. And that's a great question. So I would say that, of course, if you think about this in 3 dimensions, this is quite complex. And there are models which try to capture that complexity. But what happens is that those models are so complex and so time
You
intensive.
overfit the data, you end up overfitting it. I mean,
Yes.
essentially, it's not worth it. That's what you're claiming, that there's too
Yeah.
many parameters and you can end up fitting
Yeah.
anything.
Yeah, so that's one point. And the second point is that those models which try to capture that complexity tend to oversimplify other complexities like the radiation and everything. So you
Okay.
tend, yeah, yeah.
By the way,
So,
there is a question from Suchetana in YouTube from Presidency. She asked, how is the lower limit of the temperature defined in the case of brown dwarf?
yeah, I think I answered that. And the
Oh, you did
answer,
answer that. Okay, all right.
yeah,
Okay, must have missed that. Okay, all right.
yeah, yeah. Okay. So this parameter is perhaps the most uncertain parameter, and we need to do something about this because this parameter has implications. If this parameter is uncertain by this amount, that means in our models, our chemistry is also very uncertain. This parameter also affects clouds. Our clouds are also very uncertain. So everything is not looking good as we head on to JWST time because we are going to get data which is very precise, but our models have this uncertainty. Now, how do we reduce that? And to do that, we have developed a model, an atmospheric model for brown dwarfs and exoplanets, which is called Picasso. And this would be made public soon. This is all Python based. And we, for the first time, have included dynamics self-consistently in an atmospheric model for exoplanets and brown dwarfs. Now, what does this model do? It basically, if you say you want to model your favorite planet, Jupiter, what you need to tell this model is what's the interior temperature of Jupiter, like the base value of a temperature, and what's the gravity of Jupiter. And what this model will tell you back is what the atmosphere of Jupiter is like, what its chemical nature, what its cloud nature, what its temperature nature, everything else. Yeah, in 1D, it means radially. Yeah. So since the data we get from exoplanets and brown dwarfs is always global average data because you are 1 pixel. So generally, these models are 1D.
So how about the mass?
So the mass information is basically linked to both the interior
Gravity.
temperature to evolution and also to gravity. Yeah.
Right, because I was wondering, I mean, probably similar planets of similar masses may have a similar sort of abundances, because you
Yeah.
have to have some starting assumptions. Otherwise, you can't
Right.
really build a
Yeah. Totally.
constant atmosphere, right? So, yeah.
Yeah. Yeah. Yeah. So yeah, we have this model, and let me show you an example of how this works. So this is just showing you the iterations in the model. I have tried to model some brown dwarf with some properties, and you can see that this model takes care of all the physics interconnections between temperature, chemistry, clouds, and everything, and iterates all of that at once to give you an atmospheric state, which is physically consistent at the end. Okay. Now, why is including dynamics in this model important? Because dynamics affects chemistry. And remember, everything is linked to everything else. If chemistry gets impacted, the radiation field gets impacted because of absorption. That would lead to impact on the temperature pressure profile. For example, here, the dashed line is the temperature pressure profile of a brown dwarf if it did not have dynamics, and the solid line is when it has dynamics. So our model takes care of these dependencies as well. And I would come to why that is important here. Now, in 2020, one of my fellow grad students at UC Santa Cruz actually tried to measure this parameter KZZ in some brown dwarfs, 6 brown dwarfs. And this is what this plot shows. Y-axis shows KZZ, x-axis shows temperature of those brown dwarfs. And those dashed lines, those show the KZZ, what you expect from total convection or free convection. And what you see here is suddenly in these brown dwarfs between 400 to 800 Kelvin, the measured KZZs are 2 to 3 orders of magnitude lower. That means somehow suddenly these brown dwarfs do not have as much dynamics as what is expected from basic theory. Now we were curious that why that is so. And one hypothesis is that if your brown dwarf does not have one convective and one radiative zone, but 2 of each, if you have a radiative zone in the deep atmosphere, like a sandwiched radiative zone, then what can happen is your radiative zone has low dynamics, right? Your radiative zone does not have this convective wave. So things are slower here. And if a gas gets quenched at this radiative zone, as an observer, you would interpret that the whole dynamics is slow, basically. So if you have this sandwiched radiative zone, then things can look as if KZZ is low because you are measuring the KZZ at a radiative zone. Now, this is a wonderful opportunity because this means that if this happens, then we can actually measure the KZZ at the radiative zone, which was uncertain by 8 orders of magnitude. So if this is a physically true picture, then this is a great opportunity to measure this very uncertain parameter and constrain. And this is exactly what we tried to look at with our model. So this is a plot showing in the y-axis the gravity of your brown dwarf or your gas giant planet, and in the x-axis the effective temperature. And this is actually from an earlier class of models, atmosphere models, which did not have dynamics. And the question is whether this second radiative zone, first of all, exists or not. Is this just an hypothesis, or this is physically true that this second radiative zone can exist? And from earlier class of models, we see that everything you see in yellow here and not this blue are objects which could have this second radiative zone. But see here that those objects do not have temperatures from 400 to 800 Kelvin. From about 550 Kelvin, this second radiative zone does not exist. So these models cannot explain your observations because in observations, KZZ was low between 400 to 800 Kelvin. So we, with our model, tried to do the same thing, but this time by including the dynamics in the model self-consistently. And by doing that, magically, the second radiative zones started appearing at the correct temperature. So, yeah. Oh, that's just gravity. Log of gravity, like 10 meters per second squared. That's the log there.
I mean, one more thing is that why are the plots not smooth? Why is it like?
Yeah, that's because this is a grid of models, and yeah, so there's a grid spacing. Yeah.
But like, why can't you have lower grid?
You mean like smoother?
Yeah, smoother.
Oh, you can do that. Like, there's no problem with that. But this is like the grid spacing is 25 Kelvin basically. So this is not a huge parameter space. So that's right. Yeah.
So it's like is enough to
Yeah.
understand.
Yeah. So as I was saying that when you include dynamics, yeah. Yeah. Yeah, so these, what I'm talking about is much deeper than the exosphere. So the exosphere is at pressures of 10 to the minus 6 bars or even lower pressure. Yeah, and here I'm mostly talking about all the things which happen between 10 to the minus 4 to hundreds of bars. Because that's what you can mostly observe. You cannot mainly observe exospheres in exoplanets. Yeah.
But you are also sure that exosphere doesn't have any active impact also on the values of.
Yeah, they might have, but I think they're not that important yet in this context. Yeah, they might have some impact. Yeah. So yeah, the good news is that this second radiative zone exists, and it exists at the right temperatures only when you take dynamics into account. Taking dynamics into account is important. But remember, having a second radiative zone does not guarantee quenching at a second radiative. You can only make that measurement if things are quenched in the second radiative. For example, here, CO is quenched in the second radiative zone. But look at CO2, it is still quenched in a convective zone. So if you measure the CO here in this brown dot, you can measure the radiative zone KZZ, but if you measure the CO2, you can measure the convective zone KZZ. So we also needed to look at whether things are also quenched in the radiative zone. And this plot again is the same parameter space, and it is showing you the amount of CO in their atmosphere if you did not have any dynamics. And as you guessed, you do not have any CO because you do not expect that. Now, once you include dynamics, you tend to get a lot of CO because things are dredging up. Now, everything which is hashed in this diagram are objects where CO was quenched in the radiative zone. And everything which is not hatched here are objects where CO is quenched in the convective zone. So that means with our model, if you measure the KZZ or if you measure observe these objects, you can measure their convective zone KZZ. And if you observe these objects, you can actually measure their radiative zone KZZ. So we verified with our models that this is something doable. We can go out there and constrain the KZZ both in the convective zone and radiative zones of brown dwarf. And let's look at all of this effect on spectra, which is the observable. So here in both the panels, I'm showing you the spectra of the same brown dwarf, but with different amounts of dynamics in the radiative zone. And you can see that there is significant observable difference in fluxes, which you can measure. But the problem is, from ground-based observatories, Earth's own atmosphere is very bright in these wavelengths because of its own temperature. So you cannot do a good job with Earth from the ground-based telescopes. But we still can try, and that is what we did. We applied our model to some Keck, Gemini, Spitzer data and tried to measure the KZZ of those brown dwarfs for which Miles et al. Had done previously. Try to see if we can measure their KZZ. For example, in this case, this is the best fit model to the data, and these are the best fit model physics, the temperature structure, the chemistry, the time scales. And you can see that you get a radiative zone quenching here, which means that we have measured the KZZ of this object in the radiative zone for this object. And you can make a similar plot here with KZZ versus temperature. And with our modeling approach, we found that these four objects had really low KZZs because they actually showed radiative zone quenching. And these objects showed convective zone quenching, but still they are low, which exactly proves Dibyendu's point that these objects have, even though they are convective zone quenching, but they are still off from the maximum convection by a large extent. And maybe that's where the complexity of the convection lies. We still do not understand that complexity yet in these objects. But let's come back to JWST. As I said, JWST is an infrared observatory. And good news is it's not on Earth. It's far away from Earth. Plus, it's very cold. The JWST has been cooled down to very low temperatures so that its own black body radiation does not get captured by its own detector. Because that's what tends to happen in the infrared. So it's a very cold and a very big observatory out in the space. And because of the size of its mirror compared to Hubble, for example, its size is 6 meters. 6 meters is very large. That makes it very large light collecting area so that it can see faint sources. It has a lot of, it's also very reflective in the infrared. So with all of these advantages, JWST is a much more sophisticated instrument than anything before in the infrared wavelength. Let's see what JWST can do for this field. Oh, here I have an image of the same field of stars taken with Spitzer on the right, which is the more true predecessor of JWST, and JWST in the left, and you can see the difference. Images are crisper, backgrounds are lower, fainter sources are visible. So JWST is really powerful. Let's see what it can do. Yeah. Uh-huh.
How is your dynamic modeling done, and is there any turbulence involved in your dynamics?
Yeah, so the dynamics model does not specifically include very detailed microphysical physics basically. It's an 1D model with the diffusion phenomenon, and all your microphysics, all that ignorance is captured by that parameter. So it does not really give you a turbulence or anything. It's basically parameterizing all that ignorance in uh, a reasonable way, basically.
So you don't have any electric correlation in
No, no. But KZZ can vary as a function of height, but there's not really a random perturbation there. Mhm. Yeah, that's a really good question. So this modeling framework can totally be used. In fact, in some cases, it has been used to model TRAPPIST-1 planets, which are expected to be terrestrial. This specific model has been applied there. But what you just need to do is change the lower boundary condition, because in case of gas giants, you have eternal gas, whereas in case of terrestrial planets, you have some surface which would be reflecting and absorbing some amount of radiation. So yeah, this framework was used to first calculate the effect of carbon dioxide on global warming on Earth, for example. This same framework. Anyway, so coming to JWST. So imagine you have a brown dwarf with 3 different amounts of dynamics in the radiative zone. That would lead to 3 different spectrum in the M band. And let's see what JWST can do. So JWST has this instrument called NearSpec, which is basically a spectroscope. And just with 2 minutes of exposure time, it can clearly distinguish between these 3 cases, which means JWST with 2 to 10 minutes of exposure can constrain this KZZ parameter. When it's combined, the data is combined with models like ours, it can lead to constraining of this KZZ parameter, which has been uncertain for so long by so much. So JWST is like magic in this case. This is again a zoomed in view. So this panel shows you the signal to noise in the difference. So just with 2 to 3 minutes, you get a signal to noise of 5. But if you invest 15 minutes, then this will rapidly go up. So JWST can do a lot in constraining this parameter. Other than that, JWST will also look at a lot of transmission spectra. It can constrain the temperature structure of the planet, the chemical structure of the planet, clouds in the planet. And I and my group back at UC Santa Cruz and NASA Ames is working with the early release science team, who will be the first team on July 12th to analyze that data and fit these models to those data sets for brown dwarfs and exoplanets and constrain their atmospheres to unprecedented detail for the first time. So that brings me to my conclusion. So how vigorous are dynamical processes in these atmospheres? So we have developed this open source modeling grid or modeling code and used ground-based data to have some constraints on mixing in some brown dwarfs. But we are now prepared to work with JWST data coming up this July 12th, and our work has shown that it can be used to actually constrain this KZZ parameter, which was uncertain for so long and by so much. And with that, I would like to thank you with a beautiful Juno real image of dynamics in Jupiter's atmosphere. It's not working great, but yeah, it's something. Thank you.
Okay, then. So, please feel free to ask anything if you would like to know from him, or any comments on his work. Please.
Yeah.
I have one question. I think KZZ is a function of lambda, right? For different wavelengths, we get different.
Not strictly, like that's not we generally think about it, because dynamics, like your atmospheric dynamics, should not be a function of wavelength, right? It's just motion.
So within that sandwich
Radiative zone. Right? Yeah.
KZZs for different species almost constant.
Okay, so you mean is KZZ different for different chemical species? Yeah, that can actually happen. That can happen due to very complicated 3-dimensional reasons. I also do not generally understand them well, but to be very honest, theoretically that can happen. But to be very honest, the amount of data we will have right now, the quality of data, even with JWST, perhaps won't be able to tell that difference. It will be a very small difference.
any more questions from the online audience, please, if you would like to ask anything?
I had a question.
Yes, please go ahead.
So now that we're looking at the dynamics, is it possible that we can find patterns from multiple planets and then classify the type of dynamics happening on different planets, and then maybe find out how these planets were formed by the dynamics happening in the atmosphere?
Yeah, that's a really good question, and that's perhaps the goal. And as you mentioned, that we are actually now thinking of a JWST cycle 2 proposal, which would look not just at some planets, but a population of planets and try to characterize their KZZ. And it's a bit hard for me to make the connection between atmospheric dynamics and formation, but sure, we can look at the diversity of dynamics in these atmospheres with JWST. We can definitely do that.
All right.
Mm-hmm.
It shows spectra for disequilibrium, chemical
Yeah.
disequilibrium and for equilibrium.
Right. Yeah.
Like it was based on observation.
Oh no, that was just model.
So that's the model.
Yeah. Yeah. I think you were talking about.
Actually, it was not
Okay.
so I think it is saying it was population, so did you understand how you?
Oh, okay. Oh, I was saying that it can be detected observation. That difference. Yeah. But those are all models.
You can see a different spectra for disequilibrium,
Yeah.
chemical disequilibrium, and for what it would have been.
Yeah. Oh, you mean like from the same planet having two spectra? No. Basically, if you look at some spectra, you can tell if it's disequilibrium or if it's equilibrium. Yeah. 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 Yeah.
What are the
Yeah. Basically, the pressure width in pressure of the secondary tube. No, it's not. It's just, yeah, if you're asking if it's because of one, yeah, it's just magic, some unit magic. Yeah, it's not normalized. Sorry?
Log delta B is going from 0 to 1. That means delta P is basically from 0 to
Yeah, the delta P is in bars, basically, pressure difference in bars. So there's not much of normalization here. It's just like how it worked out, basically. Yeah.
Any more questions for Sagnick?
Yeah. Yeah.
Okay, then, so it's not like, let's thank him again.
Yeah, thank you. Thank you. Yeah, thank you. I think this is your last. Yeah.
So Sagnick, Sagnick, I have a question. So with JWST, is there any hope of actually doing direct measurements of spectra from planets, or you are still looking at transmission spectroscopy mostly?
Yeah, I think JWST's primary goal, like JWST will easily do transmission spectroscopy, but you can also do thermal spectroscopy from the secondary transit, right? When it's behind.
Right, right,
So
right.
that JWST will be able to do. But in terms of directly measuring the thermal light, JWST will be able to do it, but for very select few cases. I think it's more easier to do direct imaging from the ground than what JWST will be able to.
Of course, you need much bigger telescopes for that.
Yeah.
The other question is for JWST, the data that's going to come through in the beginning is that uh, uh, publicly, is that going to be publicly available, or is this going to be made available much later?
So the first set of early data release will happen on July 12th, which will be publicly available. And then there are some even geo proposals who have made the case that we will make our data public immediately. So some amount of data from geo proposals will also become public right when it's observed. But most of them, the geo proposals, most of them will be proprietary for some period. But yeah, the
Right.
first set on July 12th will be public.
Okay. So in principle, I mean, people who are interested can get their hands dirty and start learning the business.
Totally. And
Okay.
the
Alright.
team we are working with, the ERS team, their basic job is to so that they have that's a big collaboration of more than about 100 people, and they will all take a crack at the data and try to find the best reduction pipelines and how to use that data so that everyone else can reduce the same data differently or whatever. So that's their main goal, so that everyone can reduce the data.
Okay. All right.
Yeah.
Thanks. That was a very nice talk, and I appreciate that you took the pains to really go down to I mean the basics and explain things in a simple manner.
Right. Yeah. Thank you. Thank you for inviting me here. I really enjoyed
Yeah.
doing the talk. Yeah.